So, welcome to the third lecture of the third week. So, now we are progressing in the sense that just like we have spoken about second derivatives in calculus of one variable, third derivative, nth derivative, we are now going to speak about higher derivatives in this setting, that is higher order partial derivatives. So, for example, suppose you have del f of del x. Suppose you consider function f to be a function of two variables for the time being, f is x y, and you consider del f del x. This del f del x is also a function of x y, x and y, and this is what you know. You do not have to be told this, because we have seen in our examples that that is what happens. Now, suppose I say that okay, now this is a function of x y which I want to differentiate again and find the partial derivatives. I can say okay, I can find the partial derivative with respect to x as well as with respect to y. We can do this. It is absolutely a legitimate operation. Then the resulting partial derivatives are partial derivatives of higher order or second order partial derivatives, that is del del x of del f del x is denoted as del 2 f of del x 2 or del 2 del x 2 of f, whichever way you want to. Speaking about this is a matter of choice. Similarly, here you have del 2 f del y del x. You need not stop at this point, because you can always also talk about del f del y. When you can talk about del f del y itself is a function of x and y. So, you can write del del x of del f del y and del del y of del f del y, and both of these operations are absolutely legitimate, because you are just finding partial derivatives of a function of two variables, which happens to be itself a partial derivative of another function. So, this is written as del 2 f del x del y and del 2 f del y 2. So, these derivatives del 2 f del x del y and del 2 f del y del x, these are called mixed partial derivatives. This is called mixed partial derivative. So, first with respect to x and then with respect to y, mixed partial second order mixed partial derivative. If I want to be very erudite, I should say second order mixed partial derivative. Similarly, here this one is called again second order mixed partial derivative. An interesting question, an intriguing one is when does one have del 2 f del y del x equal to del 2 f del x del y. Let us see through some examples whether this happens or not, or it is always different. So, this is the question, when does this happen, when can we say that these two are equal, because that has its own advantages. I will choose example from the exercise in this book and then let me try to figure that exercise out. So, let this exercise, the function is f of x y is cosine of x square into y square. Very intriguing looking function. Now, so f x, so it is function of two variables when x and y are of course in real line, they are elements of R. So, I want to first find del 2 f del y del x, the first case, and I also want to find del 2 f del x del y, second case. In this case first we evaluate, so let us do the side rough work. So, we have to first evaluate del f del x and see it is a function of x and y. So, what is del f del x? It is minus sine of x square y square into 2 x y square. So, I can write this as minus 2 x y square sine of x square y square, because the first, this is a chain rule, it is an application of the chain rule just for the variable x. Now, once I do it, I now you see it is a function of x and y. Now, I want to differentiate it with respect to the variable y. So, I want del del y of del f del x. But if I want to do this evaluation, I have to observe here I do have a product form of two y's, function of y's. So, first I say I will take this one. So, it is minus 4 x y into sine x square y square plus of minus, so it is minus again 2 x y square into cosine of x square y square into 2 y x square. So, finally, what you get is del 2 f del y del x is equal to minus 4 x y sine x square y square. Okay. Again, if I multiply this, I will have x square here coming out. So, it is minus 4 y into, so x cube y cube cosine x square y square. So, that is what you get as an expression. So, let me write it down as minus 4 x y sine of x square y square minus 4 x cube y cube into cosine of x square y square. let us see whether this matches or not. If it does not match, maybe my calculation is incorrect or it does not match, it may not always match. So, let me do the other part here. So, what is del f del y here? Del f del y is, now we can do the calculation faster, the minus sin x square y square would continue to remain, with the fact that I will now do the same thing, but I will have 2 x square y, right, because now I have taken derivative with respect to y. So, now if I want del 2 f del x del y, now I am taking with respect to x. So, when I am taking with respect to x, first I am taking with respect to this. So, I will have minus 4 x y sin x square y square. Then I do the opposite, then I have, there is a symmetry if you observe. Then I take it with respect to the sign would become cos and negative sign would remain. So, minus cosine of x square y square into, now I am taking with derivative with respect to x. So, it is 2 x y square into 2 x square y. So, what I am finally getting is minus 4 x y sin x square y square minus, if I multiply this, I have 4 x cube y cube into cosine x square y square, and that is it. So, you see that finally, if I did the calculation, if I write down what is it, what was this, then I have this to be also minus 4 x y sin of x square y square minus 4 x cube y cube cosine of x square y square. You see, so this actually works, that okay, we have a case where the equality holds. The question would be, when will such an equality always hold? That idea was first given by Euler when he was trying to look for some results in fluid mechanics, the continuity of partial derivatives, right. Let us write down Euler's theorem. For higher dimension, this the result that we give here, for higher dimension it was given by Schwarz and Young. It is sometimes called Schwarz theorem and sometimes called Young's theorem. I have always remembered it as Young's theorem. So, let me just, for function of two variables, it just is Euler's theorem. So, what is Euler's theorem? If z equal to f x y has continuous second order partial derivatives and mixed partial derivatives. So, the partial derivatives is del 2 f del x 2, they are just called partial derivatives of second order, while this is just called a second order partial derivative. Just to put in some terminology. You know, second order partial derivatives, why we are learning it, because they will be helpful in detecting maxima and minima, which we will come in the next discussion. So, we are trying to get ready for that. So, if I have continuous second order partial derivatives and mixed partial derivatives then these functions, the derivatives themselves are continuous functions of x y, then del 2 f del y del x is equal to del 2 f del x del y. Though I intend to, but I would like to go through the proof of this step by step. So, what I will do is that I will first write down the proof on the board step by step and then try to explain to you what has happened. So, I will ask the cameraman to just hold on for a while, I will write the proof on the board and then explain to you step by step, because the proof, if I just keep on explaining to you, you may not find it very comfortable. So, one needs to understand the proof of this to see how arguments are made in functions of higher functions of more than one variable. So, थोड़ा close कीजिए. So, now you see, look at the board. I have already written down the proof beforehand. The idea is to tell you that if I just try to write down the proof and try to explain to you, you might get confused. So, we will start from the left hand of the board and then come down to this end. Hoping that you are able to see it, I would also personally go ahead and try to see that you can see this thing. Now, what we do is that we show that at any given point x naught y naught in R2, any point that I give you, if these partial derivatives, these mixed partial derivatives and second order partial derivatives, hence all first order partial derivatives are continuous, then at every point if I compute del 2f del x del y and del 2f del y del x, these two values must coincide, they must be equal, and that is exactly what I want to say. So, I start with a point which is any arbitrary point and show that for that this will be true, and once I can show that this is true for a given point, then for I can do the same logic for any point, and hence it will be true for any point, and that gives you the general result. So, whenever I am writing this kind of general result, when I am writing this kind of general result del 2f del x del y del x del 2f del x del y means they are evaluated at every point, whatever point you evaluate these two will be equal, that is the meaning, and that is the meaning that I want to carry forward here. So, here our job would be today to do this proof, and indeed of course I can talk to you about partial differential equations etc., but since this course, none of my calculus courses involves differential equations is a completely different ball game and you need to study them separately, and we will not involve differential equations in these courses. So, what I will do is the following. Let me start to explain to you this proof, but it will be very counterintuitive. This proof is from the book which I am following, the book by, again if those who are coming late into the course, again I show you this book very clearly. It is Basic Multivariable Calculus by Marsden, Tromba and Weinstein, published by Springer, a very good book for a first course. What I am trying to say is this proof was done by Euler to study some issues in fluid mechanics, but this proof has a counterintuitive feeling. Given this problem to you, it will be difficult for you to really figure out why I should start this proof in this way. See, the idea here behind the proof is that we will show that both, sorry, there is a kind of mistake here, this will be del x del y, sorry. I am just making some corrections, sorry, there is a mistake, writing mistake. So, if you look at the proof, what I am going to show that del 2f del y del x at x naught y naught is equal to some quantity, and del 2f del x del y at the same point is equal to that same quantity, and hence they must be equal. The proof actually relies completely on the Lagrange mean value theorem. The Lagrange mean value theorem, which you know for one variable calculus, which you have been taught in one variable calculus. You can go back and see my lectures on Lagrange mean value theorem in one variable calculus, and that itself gives you a quite detailed understanding of Lagrange mean value theorem. So, you can actually apply it here. So, what I do is first start defining a quantity called S of del x del y. So, I fix this x naught y naught for the time being, and I define this quantity in this way. So, what I do with x naught, I add this del x, that is an addition. I have changed y naught, I added this, then I do this and I do this and I do this. So, del x and del y is my variables here, I can keep on changing them. So, I keep on changing them, this because x naught and y naught is fixed. So, the only thing that this function can depend on is del x and del y, and that is how I have defined. Now, if I can hold y naught and delta y fixed for the moment, then if I look at this quantity, if I define this quantity gx is f of x y z naught plus delta y f of x y naught, then this quantity, because I have fixed y naught and delta y, just becomes a function of y, sorry, a function of x, because y naught and y are fixed, this quantity becomes a function of x. Now, if I write instead of x, I can put any value of x. If I put x naught plus delta x, I will get this part. If I put just x naught here, g of x naught here, I will get this part, this minus this, I will put it in the bracket. And so, S of delta x delta y can be represented as a difference of two functions, difference of values of values of the function g at two different points. So, when you can write the as a function the whole thing as a function of two different, difference of one variable function at two different points, then I can apply the Lagrange mean value theorem, because here, because this partial derivative exists and it is continuous, I can take the derivative of this, which is nothing but the partial derivative of this minus the partial derivative of this with respect to x, because y naught and delta y are fixed, you can put any number there. So, they will be fixed, you do not change them. So, if you do so, then here I can apply the Lagrange mean value theorem. So, which will say that the difference between this and this is nothing but delta x. So, g dash of some xi into delta x, where xi is a number lying between x naught and x naught plus del x. This is exactly what Lagrange mean value theorem says. So, here we have applied Lagrange MVT. Please take a careful note of this, that we have here applied the Lagrange mean value theorem. Now, what is g dash xi? Which is nothing, g dash x is the del f del x at that x minus del f del this partial derivative of this function with respect to x. So, it is del f del x so g dash xi is del f del x evaluated at x xi here, del f del x evaluated at xi here, and that is what you get. So, whatever y naught and delta y you figure out, right, you can always write it like this. Now, what is happening? Now, you have xi and you have now this y naught and delta y are fixed, but now we have also fixed xi. Now, I can look at this function del f del x as a function of two variables, but once I fix xi, I can think of this part as a function of the variable y evaluated at the point y naught plus delta y and y naught. I have actually kept them fixed, but these are 2 points where I have evaluated these 2 functions, but xi is now fixed, xi is already known, so it is fixed. I fixed the x part. Here this is also fixed, but I am not bothered now about the x part. I am looking at it just as a function of y, and I have evaluated it at 2 points. Then I can apply on this the mean value theorem again. So, my derivative of this would be in terms of the y. So, del y of del f del x, so del 2 f del y del x evaluated at some point eta, which lies between y naught and y naught plus delta y into delta y. So, this is here I have applied the Lagrange mean value theorem here and into delta x, which was already there. Delta y, del 2 f del y del x is continuous as a function of x y. So, you have if you have a continuous function, I am just writing it. So, if f x y is continuous, then f x y limit x y tending to x naught y naught, this simply means f of x naught y naught, that is the meaning of continuity. We have already studied continuity of these functions of 2 variables, and that is exactly the meaning of continuity, that whenever x y is going towards x naught y naught, it should give me f of x naught y naught, does not matter whatever be the path. Now, here what is happening is that this is continuous, which means what is happening, x y is going to x naught y naught, which means when I am taking the limit, I can actually push the limit inside. So, I can write this whole thing as f of limit of x y is equal to f of x naught y naught, which is natural, because limit of x y is what? When limit of x y when x y is going towards x naught y naught is x naught y naught. So, that will give you x naught y naught. So, when you have a continuity operation, the limit of this will take you to f of x naught y naught. That is the meaning of the continuous operation, that the function and the limit can be exchanged. Okay. So, this is what you know about from continuity, continuous function. So, this is a very important property, which this is a very basic definition, it comes from the basic definition, and that is what it is. We have studied this earlier. Now, I know that this is a continuous function because that is given to me as a statement of the theorem, right, that has been given already. Now, once that is given to me, what I will do, that I have it like this, and I will take this, because this del x and del y are non-zero quantities to begin with. So, we will mention, we have not mentioned it, but tacitly we are taking that these are non-zero quantities. If it is 0 quantities, then it is nothing, then it is just everything will cancel out, it will become 0, right. So, we will not bother about that, we are talking about non-zero del x del y. So, I am dividing this side, I am bringing del x del y to this side, dividing both sides by del x del y, I will get this is this. Now, if I take now what I will do, I will take limit on both sides as del x del y tends to 0 0. Now, if you observe, if del x del y tends to, sorry, this is del 2f del y del x, as del y, where does xi and eta go when del x del y is pushed to 0 0? Basically, if you just take x naught to be positive for the time, x naught or y naught both positive, does not, just for an explanation, you have y naught and y naught plus delta y, you have xi you found somewhere here, eta you have found somewhere here. Now, when you push make delta y 0, y naught and y naught plus delta y both coincide, because but xi and eta or x naught and x naught plus delta x both coincide, because xi is lying between them, it will be sandwiched between them, and they will also approach x naught, because when delta x goes to 0, if they are made smaller and smaller, because this story that this will be divided by 1 by del x del y, del 2f del y del x evaluated at a point xi eta, where xi is a point lying between x naught and this, and eta is a point lying between y naught and y naught plus delta naught. This will be true for whatever del x del y non-zero del x del y you choose. Now, if you make them go towards 0, make them smaller and smaller, then xi and eta would be also, because the sandwich between these two quantity would be forced to go to y naught, because x naught plus delta x goes to x naught as delta x goes to 0, and y naught plus delta y also goes to y naught as delta y goes to 0. So, xi and eta means as they are sandwiched between these two, they will be also pushed towards x naught and y naught. So, as delta x delta y goes to 0 0, xi eta is going to x naught and y naught, and by the continuity of this is nothing of this of the second partial derivative, mixed partial derivative, we have del 2 f del y del x is x naught y naught. Why you needed continuity of all the kinds of partial derivatives? Because see, because if the second partial derivatives or first partial or second partial derivatives are continuous, the first partial derivatives are continuous. Because of that, you can actually compute this thing and you can write down g dash xi, and because of the continuity of the second partial derivatives, you can write down this, right. So, without the continuity, because once this is continuous, the others are continuous, without the continuity of this derivative, you cannot put this x naught y naught. In this limit, you cannot say that this limit is this, because this when it goes to 0 0, xi eta is going to x naught y naught, and that by continuity, by this thing, you will have this, and this is the limit. So, this being a finite quantity, this also has to be a finite quantity, because both the limits are equal. Now, what you do? So, you prove that del 2 f del y del x evaluated at x naught y naught is something like this quantity. Now, you change the role of x and y, you change the role of x and y. So, in fact, you define g tilde y as f of, instead of x, f of x naught plus delta x y minus f of x naught y. If we define it, then what would happen? Then s of delta x delta y that would be written as, if I put g tilde of y naught plus delta y. So, g for y naught plus delta y. So, this minus this plus this minus this. So, minus g tilde of y naught. So, what is g tilde of y naught plus delta y? Here you will have y naught plus delta y, here you will have y naught plus delta y. So, you will club these two together and you will club these two together, and you will have the same story being told, and you will be able to show that del 2 f del x del y at x naught y naught. It is a homework for you, you can try this by the same logic, is exactly equal to this, and in that way these two are equal. In that way these two are equal, because these two finite quantities are equal to the limit of the same limit, which has to be finite. So, that is about it, and we end our talk here, hoping that you get an idea. This is a very important concept, that the equality of mixed partial derivatives. This plays an important role when we will do optimization or minimization or maximization of functions, and then that is what we are going to start tomorrow. Thank you very much.